Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. So this is lecture number 37. It's been a while since we had a tutorial. Probably, we had tutorials in as part of lectures 23, 24, something like that. So this will be tutorial 7 as well. Our top, this lecture 37. All right. So we'll continue with our practice of solving problems. I'll be giving the problems on the board and we shall be solving them together. And the concepts, that we looked at after the last tutorial include black body radiation, the idea of wave-particle duality, which led to the black body radiation problem getting solved, introductory quantum mechanics as necessary for astrochemistry, and we also looked into some fundamental properties of light, light being a wave, particle, properties of waves and particles, matter, some de Broglie expressions, etc., etc. We also looked into some aspects of electronic spectroscopy also, right? Some introductory aspects of electronic spectroscopy, the ground state, the excited state, and all of that. All right. So we shall be solving some problems based on all this content as relevant to astrochemistry. Okay. Now, to begin with, the first question for today is going to be based on the idea of units and dimensions. Recall that in the black body radiation, we were plotting, something on the x-axis and something on the y-axis. What is being plotted on the x-axis? X-axis that we plotted. Is it frequency or wavelength? It's frequency, correct? Yeah. So in black body radiation, x-axis is frequency. It could also be wavelength, but that's what we saw, in our class here in this lecture. Okay. Now, what is the y-axis? You can recall from your previous lectures, the notes. It was some quantity called as rho, correct? Some quantity which I did not define, right? If you recall from the lectures, I did not define what this rho was. Now, I'm going to give you the expression for rho, okay, right? So, Planck obtained rho as the following expression. I'll just look for clarity. It is, 2h nu cube by c cube times k, where k is 1 by e to the power h nu over kBt minus 1. So this minus is now not as part of the exponent. It is like along with t. So e to the power h nu by kBt minus 1. All right. So this is what Planck obtained. Okay. I did not give you this. And did we look into its derivation? No, we did not. Okay. The key thing was I just told you that Planck used the idea of quantization, and based on it, he obtained a different average energy for each of the oscillations. And from that, he could compute that, the theoretical curve would have a maximum value and it would fall off. Okay, right? So what I never told in this class is how this expression is derived. We don't even care about the derivation for our purpose, because that would then be the proper quantum physics or perhaps, a thermal physics class. It's an astrochemistry class, so let's keep it to this. Okay. Now, given this expression, the question is, find the SI units and dimensions of rho. Clear? Given this expression, where rho is like 2h nu cube by c cube times k, right? Find out the dimension of this specific thing rho on the LHS. All right? Question is clear. Let's start working it out. I will write, both the terms together. So your rho is given by 2h nu cube by c cube times k. I'll just put it here, 1 over e to the power h nu by kbt minus 1. Now, well, each terms have their own meaning, right? As we've been consistently looking in this lecture. What's the easiest point to start with? Well, the easiest point to start with is right here, this expression, this thing, right? This fellow right here. Why is it? Because, of course, we may have to do some computations here, but it is much easier to start with this because 1 is a dimensionless number, right? 1 is a number. So with number, I can only add a number, right? So we call that only same dimensions can be added or subtracted. Which tells us that the whole thing, this whole chunk is a number, which implies e to the power h nu over kbt is just a number, right? I mean, the exponential of something is just a number, which means that this whole thing is a number, which implies the quantity I define as k, right? K, just a number. When I say just a number, I mean that it is dimensionless. Dimensionless. Okay, so I've written here dimensionless. So, in fact, you can also, if this, okay, just as a sub question, if this whole thing is going to be dimensionless, what are going to be the dimensions of this quantity h nu by kbt? Well, for h is what? E equals h nu, so therefore h is going to be joule seconds, right? So joule seconds per second, so this is going to be joule, right? And kbt. So this is just a small digression, okay, right? A small digression. We are just double verifying now. We're just double verifying that if this whole thing is dimensionless, if this thing should be dimensionless, then the units of this and this should be the same, right? Small digression. If k has no units overall, it's all. I already told you that e to the power h nu over kbt has no units. Then kbt should have the same units as h nu, correct? Now this is going to be joule, of course. How do you know that this is joule? For that, we must know what the Boltzmann constant is, right? Now kb is the universal gas constant, right? Divided by the Avogadro number. Now this is going to be Kelvin. Now R is going to be joules per mole per Kelvin. Recall from PV equals nRT. I think we used the equation, the ideal gas equation, PV equals nRT, long time ago, when we were discussing, the differences and similarities between the ISM and Earth, right? Okay. So this is joule per mole per Kelvin. What are the units of the Avogadro number? The units of the Avogadro number is per mole. Okay. Even though we call it a number, right? It always quantifies, a mole. Okay. When we say, like there is a 6.023 10 to the power 23 number of electrons, we call it as one fundamental unit of a mole. Okay. So this Na is going to be per mole. So therefore, this is, per mole, right? This is R and T. So this is going to be R. So my RT is going to be, therefore, kBT is also joules. So we understand that from whatever perspective, because we add this to this, we add this exponent to this one, which is a dimensionless number, we're not going to have any units here. But if this quantity were not to have any units, right, then even this whole thing, this h nu by kBT, that should also cancel out, right? And that is indeed cancelling out. The numerator is joule, denominator is joule. So we have e to the power something, right? So from all perspectives, right, from all perspectives, we are correct in our units and dimensions. Now, why do I spend so much time, with units and dimensions? It is because no matter what equation you see in physics or chemistry or physical chemistry or chemical physics, right, which are all connected intricately to astrochemistry, always look into the dimensions. right? Look into the dimensions and ensure that you understood the dimensions properly. Okay? All right. So let's go back to the question. So we understood that this quantity is dimensionless. I will continue here. Okay, I'll delete the question itself. So this is page 4. So I just have to worry about this quantity right here, right? 2h nu cube by c cube. Okay, as always, my 2h nu cube by c cube is going to be, h is going to be what? Planck constant, which is joule seconds, right? And nu cube is going to be, nu is going to be per second. That is, frequency is per second. So nu cube is going to be s to the power minus 3, right? And what is c? It's the speed of light or velocity of light. And what are the dimensions of it? It's meter per second, right? So this is going to be meters, but this is c cube, right? So meter per second, the whole cube, I take it in. So this is going to be meter cube, and this is going to be s to the power minus 3. Are we good? So we get rid of this, all of these quantities, and what we are left with is what is called as joule seconds per meter cube. All right. So this quantity is joule seconds per meter cube. This has no units overall. So the net unit of rho is going to be joule seconds per meter cube. This is something exceptionally important. Okay, this is in fact called as spectral density per bandwidth. That is, don't worry about the technical term, right? But we're going to be, like using this particular term rho, right? Which is also called as spectral density. Because it is a measure of, some amount of energy per meter cube. All right. So this is what is called as spectral density. The density part is coming from the per meter cube over here. Are we good, clear? So what did we do so far? What we did was, we just looked into an equation and analyzed it very thoroughly and obtained its dimensions. Okay. With this, we'll continue to the next question. This question is also going to be about dimensions. I will call this question number 2. The question is, recall the wave equation. The wave equation is right. So this is the wave equation. I want to clarify one aspect. While writing this equation in one of the lectures, I made a notational mistake. I made a typo. I put the 2 here also. That is just absurd. Okay, right? I think I wrote something as this. Of course, I clarified it later on, but please note that this is meaningless. Okay, this 2 should not be here. That was just a pure typo. I'm clarifying that aspect because tutorials are also to clarify, what was not exactly precisely covered and precisely expressed by me in the lecture sessions. Okay. All right. So this is the wave equation, and I had told you that U itself has no units. I said that, right? Now, but I asked you to ignore it, in the lectures, and that in the tutorials we shall be discussing it. Can somebody please tell me, right, how to justify it? How to justify the fact that U has no units? See, after all, if U has no unit, right, we understand that this is going to be per second square, right? And this is going to be second square per meter square. So the second square and second square get cancelled out. This will be per meter square, and this is per meter square. It makes perfect sense. But it makes perfect sense only when U has no units. How to express it? Or, like you can also have, okay, I'll whatever phrase I started with, I'll say it later. Ignore my last sentence. The sentence which I partially started and did not complete. Ignore that. Okay, yeah. So how to justify this fact that it has no unit? Give me some ways to justify it. Yeah, a good start would be that. What is this? This is after all a wave equation, right? Now, what is one way to write an equation? The wave equation can be written as y equals sine omega t plus or minus, right? Or like kx minus omega t. This is how you write it, right? Right? Sine of kx minus omega t. Clear? And what is k here? For just take the expression of starting with starting with a stationary wave, this is what we obtain, correct? So now, what are we dealing with here? We have, recall from the previous question, we discussed that, only quantities of the same dimensions can be added. Within the bracket, I'm adding a kx term with omega t. This has a time term and this has a distance term. How can they even be added? Well, the answer lies with the idea that what is k here? In the k here, if you recall from your school level physics, k is 2 pi by lambda, where 2 pi is a number and lambda is wavelength. So this is going to be per meter, right? So kx effectively what? Kx effectively is going to be having no units. That's it. We've solved the problem, because likewise for omega t also, your omega is 2 pi nu, right, which is the angular velocity, and 2 pi is, of course, an irrational number. So 2 pi is also an irrational number, by the way. Okay, if pi is an irrational number, 2 pi is also an irrational number. And what about nu? Nu is like per second. So omega t also has no units. This is no units. I mean, no units. The handwriting is not that good, but it's no space units. Okay. Likewise, omega t also has no units. So therefore, I can easily add these two, and it makes sense. And so it becomes a sign of something, right? So sign of something is also going to be no units. So it's just going to be a number. So y, or or I can call it u for the sake of notational, consistency. If this is u, so overall, u has no units. But you can ask me a quick question. Okay, but in my wave equation that I studied in high school, there was always an amplitude factor, right? There's an amplitude term right here. Well, and the amplitude has some dimensions, right? Amplitude has some length dimensions, correct? So if the amplitude has some length dimension, then this equation does have a dimension overall, right? Yes, in that case, it does have a dimension, but it gets cancelled out, because when you do it right here, right? When you write the expression as a sine kx minus omega t, right? In that case, this a, as you differentiate it twice over here and differentiate it twice over here, because a is a constant, it will come out soon. So therefore, the prefactor a, the amplitude being part of this equation, will not have any bearing on this statement, or this equation itself. All right. Therefore, whether or not we include the amplitude in our wave equation, it doesn't matter. And if you don't include the amplitude, this is going to be dimensionless, right? So you do units without amplitude, okay? Without including the amplitude. And of course, it does get some unit once you include the amplitude, but that is not a problem for this equation, because the amplitude gets cancelled out on both sides. On that note, we shall proceed to the next question. We're good, right? Okay. My next question is going to be based on my how we obtained, right, the time independent Schrodinger equation. Okay. So this is question number 3. So we've discussed, quite some amount of dimensions. We'll move along from it. So in the class, we obtained h psi equals E psi. And why did we obtain it in this class? Well, because this was the fundamental equation that could be used to describe a lot of quantum mechanical entities. That is, for example, matter, which exhibited both wave and particle nature. And why do we care about such particles in this astrochemistry course? It is because, the dimensions of these systems, right? The dimensions of these atoms and molecules match with the dimensions of the molecules of interest in astrochemistry. In other words, okay, right? The molecules that are of relevance in astrochemistry, they're all quantum mechanical entities. And that is why we care about this particular equation. Okay. We obtain this equation only for one dimension. Right? In other words, the explicitly writing it, this was minus h bar square over 2m d square by dx, where h bar is h by 2 pi psi of x plus some arbitrary v of x psi of x, and that is equal to d psi of x. Okay, this is what we had written. The question is, I told you, I mean, I was just mumbling about in the lecture that, oh, even though we see this only for a one-dimensional system, we can always generalize it to 3 dimensions, right? I was just telling you, without writing anything on the board, that instead of this d square, we can write del square, and we can just extend it. But how is it done exactly? What is done in practice? That is what we shall see in the tutorial now. Okay. So we have this statement right here. Okay, the h psi equals e psi. This is in 1 dimension. The generalization to 3 dimensions is very straightforward. How it is done is, your Hamiltonian, that is like the h, right, is simply going to become dou z square, right? And your potential form, okay, right, this is going to be plus v of x comma y comma z, right? This is going to be your Hamiltonian. Now, what was an ordinary differential term here? That is like d square by d x square. Sorry, the 2 was missing over here. Okay, please correct it. Okay, now this thing becomes becomes a partial differential equation here. Okay, the partial differential form. This Hamiltonian takes a partial differential form for the kinetic energy operator, because when it's just 1 dimension, we are dealing with the motion only along 1 direction, and so we get only 1 kinetic energy term. However, when it's along all the 3 dimensions, right, we get this term. Now, this is called as a Laplacian operator. Okay, let's not worry about the technical term, but notice that I will briefly explain the logic as to why we can separate x, y, and z individually. It is because motion along x, y, and z directions are independent from one another, right? So because the motion along x, y, and z directions are independent of one another, right, there will be 3 independent kinetic energy terms along x, along y, and along z. Therefore, all these 3 terms have to be taken together to represent the Hamiltonian for a 3-dimensional system. And note one interesting part, because motion along the x-axis is independent of motion along the y and z directions, right? We have what are called as partial derivatives here. In other words, let's say that for some function, okay, and of course the psi, okay, right, is now going to be psi of x comma y comma z. Psi is going to be a 3-dimensional function now. Now, say for example, I take this mathematical function psi of x comma y comma z to be, something like x square y z cube. Just for the sake of it. This is not going to give me any physical insight, but I'm taking it just to demonstrate the point. Now, because the motion along, my x direction is independent of y and z, right? As I get my dou psi by dou x, for example, right, I'm going to treat y z cube as constants. Okay, right? The y and z terms will be complete constants, and I'm only going to be differentiating the x terms. And so likewise, my dou 2 psi by dou x2, right, is again going to be a situation wherein the y and z are going to be kept a constant, and only the x is going to be differentiated. And so that is how I obtained this. Likewise, by symmetry, you can do dou 2 by dou I2 and dou 2 by dou Z2 also. All right. Sometimes I use the phrase dou 2 by dou Z2. Some other times I tell dou square by dou Z square. Okay. I use dou 2 by dou Z2 because I don't want you to get confused with any wrong idea that, oh, we're actually not taking a square, a square here, and we're taking a square here, etc., etc. It's just that when we speak, right, we use the phrase dou square by dou x square or something. Okay, there is no square business taking. It's just differentiating twice. All right. So this is how overall we extend. Okay, right? We extend the time independent Schrodinger equation from 1 dimension to 3 dimensions. The same can be done even for the time dependent version. I'll give that to you as a homework. It's no big deal. It's just the same way you do it. Okay? Are we clear? Yeah. So in this question, we obtained h equals d psi for 1 dimension. The question itself is how to extend it to 3D. I mean, I gave you the answer, but forgot to finish the question. Okay. So the answer begins here. And how to extend this to 3D is the question. By this, what do I mean? I'm talking about the Schrodinger equation. All right. So this is question number 3. Now I think we may have time for one more question. I will delete this part. So this question is, again in the lecture, I know when we introduced this quantum mechanics and all these things, right? I had mentioned to you that the wave function psi of x, right? If we deal with a one-dimensional system, is purely mathematical. Right? If it's purely mathematical, then why worry about it? Then why even care about it? Then why care about it? In physics, a lot of the time we keep talking about this wave function, right? Yeah, why make a big deal about something which is just a mathematical function? Physics, and also in chemistry, and of course also in astrochemistry. Right? Not astrochemistry, it's astrochemistry. All right. So the answer, what do you think is the answer? What is the obvious answer? Well, even though the psi, that is the wave function itself, is purely mathematical, we use that to get the energy, right? The answer is that we use psi or psi of x to get energy. Now, energy is, of course, a physically observable. That is, you can obtain it from experiments. Energy, and compare the E from experiments whenever possible. So, psi is a tool. Psi is just a tool. It's just a mathematical tool to obtain a physically observable quantity. All right. So that is the crux. Of course, there are other aspects of the wave function also. For example, the wave function, after certain mathematical manipulations, can give rise to the probability of finding in any quantum mechanical entity in any given volume element. Okay, right? So I don't want to even talk about those things, but overall, I want you to emphasize that the wave function, right? The wave function is a mathematical tool. Okay, mathematical tool to get an experimentally observable quantity. All right. For example, in astrochemistry, okay, if you take about astrochemistry, what is one experimentally measurable quantity in astrochemistry? We're thinking about detecting molecules in space. What do we get? We get light, right? Yeah, we get light. Let there be light. So there is light on us, right? But what do we get from the light? We get the intensity of the signal, right? We can measure the intensity of the signal experimentally obtained. Okay, right? So we get the intensity of the light is an experimentally obtained quantity. Okay. Now that could be connected with the wave function, and the wave function could be used, right? I'm not telling you how. Notice it clearly. I'm not telling you how. Maybe when we discuss about electronic spectroscopy and atomic spectroscopy as relevant to astrochemistry, I would perhaps tell you. For now, just understand that psi can also be used to get the intensities of the lines. Okay, the intensities of the spectral lines obtained, which is going to be of utmost importance in astrochemistry. Okay, so overall, your psi is nothing but a mathematical tool. I'll write this word explicitly. It's a mathematical tool. Mathematical tool to do what? To get physically observable quantities. To get physically observable stuff. I'm just putting it as stuff, but by stuff I mean physically observable quantities, such as the intensity of light in the case of astrochemistry, the energy more generally, right, etc., etc. Okay, so in this tutorial we looked at 4 questions. We started off by looking at units and dimensions, and then I told you some fundamental aspects of the Schrodinger equation, which we discussed in class. So on this note, we shall continue with our next tutorial, and we shall see more questions and answers. Thank you so much.